looking at how a malicious user can overload some target to deny the normal users access to that target. Okay, so we've started going through some scenarios. We are looking at a simple ping flooding attack where there's some target computer where the malicious user wants to stop people accessing that target computer. So the idea is that on one of the links leading to that target, especially the slowest link, or what we say the bottleneck link, try and send enough packets such that the capacity of that link is utilised, fully utilised. So that link has some capacity, that is the data rate that it supports. If we send enough traffic into this link and use up that entire capacity, then the data from the normal users will not be able to pass through that link, or at least will be delayed a lot. Okay, so this depends upon a bottleneck link being leading up to the target. And with the ping flooding attack, we use ping, which is a simple application that the source sends an ICMP Echo Request to some destination computer, and the normal behaviour is that that destination replies with an ICMP Echo reply. So the protocol used is ICMP, there's a request and a reply. That's the normal behaviour of ping. So the idea of the attacker is to send many of these ping requests to the target, not worrying about the replies. We don't care about the replies. What we want to do is just send many ping requests to the target such that we overflow this link. We fill up the capacity. Why use ping? Well, the idea is to be able to send data to some target and such that, and we'll see later when we reflect off others, such that the one that we're sending to will actually respond, or that the data will get to that target. We'll have a look and see, well, why not use, say, web browsing or sending to a website? Why not use other protocols? So we'll look at what's the benefit of using ping when we look at the different attacks. But the general idea, send us enough data to overflow the link. And we got to a point of some variations. Well, one thing is to, when we send our data, use a fake source address. Different purposes of using a fake source address. One is to hide. So one way to stop or to recover from a denial of service attack is to find out who is doing the attack and take some action against them. The action may be blocking the data that they're sending somewhere, or maybe some legal action. Okay, if this is an attack on some company, then that company can take some legal action to try and stop it happening in the future. So if the attacker can try and hide themselves, then that makes stopping the attack in the future harder. So sending messages with a fake source address is one way to hide. But we'll also use a fake source address or spoofed source address to facilitate the attack, to make the attack more powerful. And how do we do that? We'll skip back to some slides where necessary. This was an example where the attacker sends the ping messages, sets the fake source address such that A, the target doesn't know where they come from, so to hide, and B, such that the traffic doesn't all come back to the attacker and overflow the attacker's link. Okay, so it goes to others. So that was using a fake source address. So the attacker sends a message, the target receives and replies to others. But we'll move to a more powerful attack in that send the message to normal computers on the internet, so just some other random computers on the internet, with a fake source address where the source is that of the target. So this, we send a ping echo request to this computer, this one receives it, and this one looks, okay, I just received a message and the source address was from the target IP address, therefore I will send a reply to the source, so I'll send a reply to the target. And the attacker sends similar pings with this fake source address set to the target to many computers on the internet, and they all reply with a ping reply to the target. So this is, we are reflecting the pings of these normal hosts in the internet. And this is a typical form of a denial of service attack. Now, from the target's perspective, does it know that it is under attack? Well, in the previous case, from the target's perspective, it's receiving pings from multiple different source addresses because they have a fake source address, so it's hard to tell that it's under attack because it's receiving pings from many different computers. And the same in this case, it's receiving pings from different computers. And in fact, the ISP of the target is receiving the pings from many different locations, different paths across the internet. So it's quite hard to tell whether this is just normal users sending traffic or if it's the attack. Of course, we can scale up, and in this example we just use 3, but use 300, 3,000, thousands of nodes across the internet to increase the magnitude of the data that comes into the target. So we bounce messages off normal hosts. Now, let's look at the applications that can do this before we look at a more detailed example. For this to work, this reflector attack, what do we need? We need these normal computers to be able to respond to the message that they receive. Now first, these normal computers are not infected in any way. So they don't necessarily have any virus or any malicious software on them. So they're not under control of the attacker. They're just normal computers on the internet. Okay? So we need a protocol such that if we send a message to these normal computers, they will respond. Now, that limits the set of protocols that we can use in such an attack. If we were using, say, HTTP GET requests, we're trying to use web browsing as the protocol here. From the attacker's perspective, if they send a message to a web server, then how many normal computers in the internet run web servers? Not many. Okay. But most normal computers in the internet respond to ping requests because it's a typical behavior of a computer that built into the operating system. If you receive a ping request, you send a ping reply. Most computers do that. But not many computers run web servers. So that's why we use ping here. Because most normal computers will respond, the attacker sends a message to them, they receive a message, so they respond. Now we're omitting information that we're going to cover later about firewalls and so on. We're assuming that they can be reached. So ping is very easy to use because most computers will respond to it. Whereas other applications, web browsing, emails and so on, not all computers will respond to an unsolicited message that they receive. Remember, the goal is to overflow the capacity of the link to the target so that the normal traffic doesn't get to the target. How do we do that? Send to many different normal hosts so that they all reflect to the target. So the more hosts the attacker sends to, the more is going to go to the target. So send to more hosts in the internet. That's how you increase the traffic to the target. Or the other way is to get these hosts to send a lot of data to the target. Okay. It's all about getting as many bits per second to the target as possible. How do we do that? Get more messages going to the target and or get those messages to be larger. And some real attacks in the internet, denial of service attacks, try and take advantage of the fact that some protocols, the response will be larger than the request. That's what I'm trying to show in this diagram. And it's not necessarily with ping. It doesn't work well with ping, because in ping, the request and the reply are about the same size. But in some protocols, the request is small, let's say 50 bytes, but the reply is large, say 500 bytes. DNS is an example, and there are a few other examples here. The idea is that the attacker, again, sends a small request to these normal hosts on the internet. These normal hosts reply, and again, we're using a fake source address, so they all reply to the target. But the idea is that the reply will be larger than the request, therefore increasing the amount of bytes that go to the target. And making it easier for the attacker, because the attacker's network doesn't need to have so much capacity. If you note, if the request and the reply are the same size, let's say the capacity of the link that we want to overload is 1 gigabit per second, then the attacker needs a link here that supports at least 1 gigabit per second, because the attacker needs to send out at 1 gigabit per second such that these will send in at 1 gigabit per second. But if the reply is larger than the request, then to send at 1 gigabit per second in, we don't have to send necessarily at 1 gigabit per second out, because we send at a small rate out, small messages, but these hosts that receive the request effectively amplify the data that's sent to the target. And this is called an amplification attack, or the concept is amplification. We amplify the amount of data going to the target. And that's common in real denial of service attacks. Questions? So we'll just quickly look at some of the concepts, then go through a demo to see them work, and then return to a summary. Questions so far?
Can we send some request and to do the different, to download some data from the target and it overload?
To download some data. Now, remember, when we're bouncing off these normal hosts, for this to work, these normal hosts must respond to the data, to the packet that they receive. Now, if, let's say, my computer in the office is one of these normal hosts, and the attacker is trying to use it to bounce off my computer and go to the target, some web server, okay? Then for this to work, my computer in the office, this one, must respond to the request that it receives. Now, and similar with all computers on the internet, like all normal computers, what do they normally respond to? Well, they usually respond to pings. That's why ping is a common protocol here. That is, most computers will, when they receive a ping request, will respond. But if someone tries to get my computer to download some other file to access some website, well, that's not so common. That is, to send a request and get mine to reply, you need my computer to be able to respond to that request. So there are only some protocols that it will do that to. So unless my computer is a web server, if my computer was a web server and this sent a request for a web page and then mine sent the web page in the response to the target, then that would work. But there's another problem with that approach, is that web browsing, the speed at which you send the response is usually not under control of the attacker. And it's because of the transport protocol used. With TCP, even though we may send many requests to the web server will not send them at a fast speed to the target. It will actually slow down depending upon the amount of capacity here. So it turns out that the protocols that we can use for such an attack need two characteristics. They need these normal hosts to be able to respond. And second, usually they need to be using transport protocols which are not TCP. TCP has characteristics that it will slow down automatically if the capacity starts to get overloaded here. So protocols that use TCP are typically not used in such an attack. Because if we used TCP and we were sending fast and this was trying to send fast to the target, TCP has built-in flow control mechanisms to slow down the sending rate if the capacity becomes full. You've studied flow control with me last semester. Remember, the idea, make sure that the source doesn't send too fast to overflow the target. So TCP has such mechanisms so that it's not very useful for such an attack, because if we start sending too fast to the target, the source will automatically slow down. So the protocols that are successful in these attacks are ones which don't use TCP, so therefore they use either ICMP, like ping, or they use UDP. DNS, for example, uses UDP. Some network management protocols use UDP. And they need to be able to, the protocol or the application needs to work such that normal hosts on the internet will respond. Ping is one, but there are a few others as well. Another form of amplification attack. In this case, we send, let's come back to ping, we send one ping message to this one, and the attacker sends a ping request to another one and to another one. So let's say it sends 3 ping requests in parallel. But we have a feature of broadcast in the internet. We can send one message to a particular network, and if we use a special destination address, that message will be delivered to all hosts on that network. That's broadcast. So broadcast is this feature that you send one, so there's one from the source, but the message is delivered to all in some set, in some network usually. If we can take advantage of that, then the attack can be even more successful. And the concept is, and again it's more amplification, the attacker, let's focus here, sends one ping request not to a particular host on the internet, but to a special broadcast address which really refers to all hosts on a particular subnet. And the way that this, in theory, works is that when you send a ping request to this special broadcast address, that one message is delivered to that subnet, and then the subnet delivers it to all the hosts on there. And therefore, all hosts on this subnet receive the request, and then all of them reply to the fake source, which is the target. And we send another ping to another subnet. That message is delivered to all hosts on that subnet, and then they all reply to the target. So this is again amplification in that the attacker is sending just 3 messages, but what comes to the target is multiplied based upon the number of hosts in each subnet. Okay, that's the idea here. That only works in very special cases. There are usually some built-in mechanisms that will stop that from working. But let's have a look and see how we can do it on our small virtual network. And we'll see this one and see some of the other forms of attack. So last lecture I gave a quick demo, and we'll continue with that. And again, I'm using a virtual network, and I've added some more annotations here. There are 8 nodes in our small network, our small internet. We have a target server. This is the one we want to overload. Overload in terms of we don't want others to be able to access it. Let's say it's a web server. It has a website, and we want to stop other users from accessing that website, or at least slow down their response time. So when they try and access, it takes a long time to get a response. That's our aim as the attacker. This is our this is the target server, computer 8. Computer 7, node 7 is a router. So this is forget about the rectangle net C, this is just a switch. So think of this as the link between router and target. And this is our bottleneck link in this example. That is, we assume this link is the slowest in the whole internet, and that's the one we're trying to overload. Remember, we're not trying to overload the actual computer, we're trying to overload the link. Send fast enough such that this link is fully utilized. And I'm going to set this link to have a capacity of 100 kilobits per second. Now, that's unrealistic. In a real network, it will be much larger than that. But just for our demo, when we only have a few nodes, I'll artificially limit the capacity of this link from 7 to 8 to 100 kilobits per second. So anything that node 7 receives that is destined to 8, the speed or the data rate which it can send to 8 is 100 kilobits per second. So our denial of service attack really needs to be able to send in at a rate larger than 100 kilobits per second. If we send in to 7 at 50 kilobits per second, then the link will not be fully utilized and other normal users' traffic will get to node 8. But if we send in to node 7 at, say, 200 kilobits per second, then 7 will be sending out at the maximum 100 kilobits per second, and the data from other users will either be delayed or dropped in being sent to node 8. So this is our bottleneck. The 100 kilobits per second is just chosen so I can demonstrate it with a few nodes. We'll see the effect in a moment. Some reflector nodes. These are normal nodes, they're not infected, they're just normal nodes on the internet, and because we're using ping, they will respond to pings. They'll receive a ping and send a response to the source. Node 3 will also be a reflector, but in some demos we'll make it also act as a web browser. That is the normal host that wants to access computer 8, just to demonstrate. In fact, in the first demo, we'll use node 3 as the malicious user. Later, we'll set this as a router and another malicious user. But let's, for now, for the first demo, forget about 1 and 2. Let's say we just have this subnet and the target 8. We're going to use broadcast. The idea is node 3 is the malicious user for this first case. It's going to send a ping request to a broadcast address. Instead of sending individually to 4, 5, and 6, so instead of sending 3 packets, it will send 1 packet to the special broadcast address, and this switch will take the role of taking that 1 packet, noticing the destination is broadcast, and therefore send to everyone on the subnet. And then those that receive that broadcast will then reply to the target. That's our first attack. So web browser, well, node 3 is the malicious one, just in this demo. So, not node 1. What have we got? Node 3 is our malicious node. node 8 as our target. Node 7 is this router. Actually, we don't want node 8. What I want to show is that node 3 will send packets. Nodes 4, 5 and 6 at least should receive and then send to the target. So let's look. We're going to look at what node 3 does to initiate the attack. We'll look at maybe, let's say, node 5 and see what it receives. We will not look at what the target does. What we'll do is we'll look at the data coming into node 7 and how much goes out. Remember, the capacity here is 100 kilobits per second. We want to send enough data into 7 such that the amount coming out reaches 100 kilobits per second. We want to fill up the capacity. So let's look at 3, 5 and 7, for example. So I need to log into node 5, which is node 5 has IP address 192.168.2.23. Let's just set this up. First, we need to set a fake source address on node 3. What source address? So we're going to use a fake source address on node 3. What's the source address? Which node's address? 8. Okay. So the idea again is to send a message, a ping to the nodes in this network, and they will all reply to 8. So the source address needs to be that of 8. And the way to do it in this case, I need to remember. Maybe I have to type it. IP tables is just the firewall software. I have to remember what to type. And it allows us to change addresses of the packets that we generate. So normally we create a packet and the source address will be node 3's address. But IP tables will allow node 3 to change the source address. You don't need to understand the details of how that works right now. Post routing means after we create it, anything that's ICMP, let's use some network address translation, and this is the main part, set the source address to, and it's wrapping around now, 192.168.3.31. No. Let's try. I need a password. Did I get it correct? Okay, no errors. So this is just the way to set the fake source address. It'll be a bit easier to see. We'll see that work in a moment. Let's just do a simple ping to just one node. So I'm going to ping, just for start, a single ping to node 5, and 5 will respond to 8. Let's just see that work. And let's just make this so we can see. And on node 5, what I'll do is, just down the bottom, is run TCP dump. If it's too small, we'll eventually make sense of it. Run TCP dump so we can see, from node 5's perspective, the packets coming in and out. I'll zoom in a moment. And now let's start our ping. And with ping, we can set the interval of the ping. Let's say 2 per second, 2 packets per second, which is an interval of between the pings that we send of 0.5 seconds. So every 0.5 seconds, node 3 is going to send an echo request. And let's set the size of the request to 972 bytes. This magic number comes from the fact that when we add on headers, The total size will be 1,000 bytes, just to give a nice round number. And ping who? Ping which address? Node 3 pings node 5. Okay, just for this first demo. That is, send a ping message to here, this one should reply to here. Okay. Node 5 is 2.23. Can zoom in a little bit. Okay, we're doing the ping, and even if you can't read the details, this is node 5 down the bottom. Every ping request it receives, we'll stop it. It receives a message, the way to read this, ICMP Echo Request from 3.31 to 2.23, and therefore the echo reply goes from node 5, 2.23 to 3.31, and 3.31 is our target. So this is the reflection happening. Now, are we overflowing? Did we overflow the target? No? Yes? Maybe? How do you know? Check. Let's calculate. In this case, let's say every packet is 1,000 bytes. Okay, the ping request and reply are 1,000 bytes, or approximately. Okay, we see that's why I set to 972. So one packet is 1,000 bytes in length. In this case, we were pinging from node 3 to node 5 at a rate of 2 packets per second. 2 packets per second it sends to node 5, and therefore node 5 will send to the target at a rate of 2 packets per second. Node 5 receives 2 pings per second, it replies with 2 pings per second. So how much data is being sent to the target? If we're sending 2 pings per second, each ping is 1,000 bytes, that's 2,000 bytes per second being sent to the target. 2,000 bytes is 16,000 bits per second. Okay, bytes to bits. That is the amount of data going to the target is 16 kilobits per second. But our capacity of the link here is 100 kilobits per second. 16 should be no problem. It's not overflowing the capacity. Rather than having to calculate that all the time, let's look on node 7 and let's monitor what we receive. And there's another program we'll use, it's called IPTraf, to measure the traffic on node 7. It provides a simple graphical interface to monitor what comes in and out of this computer. And I'll just look, there are many different statistics. We'll look at the general interface statistics and we'll see why. For node 7, there are 4 interfaces. Loopback, not important. Ethernet 0 is just for this node to access the real internet. We're not going to use that. Ethernet 1 and 2 are the interfaces of interest. This is node 7. Ethernet 1, ETH1, this interface is going to receive packets. And, sorry, there's a mistake in this picture. This should be ETH2 here. Okay, this should be ETH2. ETH2 is where it's sending to node 8. So think of input to ETH1, output to ETH2. So this is a 2 here. So this software will report for ETH1 and 2 how many kilobits per second ETH1 coming in, ETH2 going out. Let's do our ping again. And just check. So it's pinging. What do we get? 20 kilobits per second coming in and out. 27. It calculates every few seconds and keeps the average over some period of time. What do we say? One ping would be 16 kilobits per second. Okay. There are, what are there? There may be some overheads in either in ARP happening. What else can the overhead be? The packet length. I can't think of any other overhead. So 16 kilobits per second is based upon our 1,000 byte ping packet, but we have a little bit more in this case. It's a little bit more than I expected, but close enough to 16. Let's see. Remember, we need to get this up to 100 kilobits per second. ETH2, it can only send out at 100 kilobits per second. So far, we don't have enough. Let's now try a better attack. Before we pinged to a specific node, now let's ping to the special broadcast address. 192.168.2.255 is a special address which means send this message to everyone on this subnet. That is, node 3 sends this message. It sends across the link to the switch. The switch sees it's a special broadcast address, this 255 address, and then realizes, okay, I need to send a copy to everyone. And it will send a copy to everyone on this subnet. 3, 4, 5, 6, 2, and 7. They'll all receive a copy because they're on this subnet, and they will reply and reply to the target. Let's try it. The reason I just realized why it was at 25 is because we're logged into node 5, I think. I'll log out. Let's hope it works this time. Let's ping. Do you want to ping to broadcast? Ping normally doesn't let you. Okay. Why? Because it's commonly used for denial of service attacks. Well, sudo. Sorry, I forgot to include the -b option. Let's do it without sudo. -b means broadcast. And now it doesn't let me again. Now I'll use sudo. Warning. Now, node 3 is sending a ping to this special broadcast address. We note node 5 is receiving it. You can see the request is being received and it's replying. How much traffic is going through node 7? ETH1 coming into node 7 is 80 kilobits per second. Coming out of node 7 to node 8 on ETH2 is 64 kilobits per second. What's happening here? Anyone want to guess? Let's write down the calculations to see. Again, what did we say? We said that at 2 packets per second, 2 pings per second. Each ping was 1,000 bytes. Means that for one ping being sent, there is 2,000 bytes, or 16 kilobits per second. 16,000 bits every second for one ping. What's happening in this case is that node 3 is sending a ping to the broadcast address. It goes to the switch. The switch realizes this message is destined to everyone on the subnet. And note, the switch realizes that the source is 3.31. So it sends to everyone, it makes a copy and sends to everyone on the subnet, including 4, 7, 6, 5 and 2. And 3 in this case. It actually sends back to 3. Because the source address is not that of 3, it actually sends back to 3. So this is the broadcast. Send 1, everyone receives. Now, when node 5 receives, what does it do? It receives a ping request, it replies. And who does it reply to? The source, and the source was that of the target. So node 5 replies. It'll go to node 7, which will then send it on to node 8. Because node 7 is the router, it will send the ping reply, which then should send it to 8. Node 6 will do the same. It replies. Node 4, the same. Actually, node 3 does as well. 3 receive the request, 3 sends on. In this case, the way that node 2 is set up as a router, it's configured that it will not reply to such ping requests. To a ping to a broadcast address, the operating system is set up so that the router will not reply. Okay, that's actually a security feature of the operating system to not reply to those ping requests. We'll return to see why that's the case later, but 2 doesn't reply in this case. Similar, 7 is a router, it will not reply. So, what's coming into node 7? Look at the lines. There are 4 blue lines and 1 red line. So each ping generates 16 kilobits per second. So the red line is coming into 7 at 16 kilobits per second, the requests. The replies from 6, another 16 kilobits per second. That's 32 coming in. The replies from 5, that's 48 if we add that. Replies from 4, that's 64 kilobits per second. And the replies from 3, that's 80 kilobits per second coming in. 80 coming into node 7. On ETH1 on node 7, we have 80 kilobits per second. What comes out? Actually, all those blue ones should come out. They're the replies. The red one is the request going to node 7, and because node 7 is a router, it would not respond. So it doesn't send anything out to node 8. Why is it coming out here? Because the source address was that of node 8. So there are how many kilobits per second going from 7 to 8? How many kilobits per second? on ETH2, which is out of node 7, 64 kilobits per second. That's what we expect. Is that what we see? Yes. Okay. So the demo is working in this one. Coming into node 7 at a speed of 80 kilobits per second, because there's also requests coming in, and coming out at 64 kilobits per second. We care about the coming out, really. 64 kilobits per second. Capacity 100. We haven't reached our capacity yet. How are we going to reach the capacity? How do we increase the amount that 7 sends out to 8? Again, put on your black hats. What are you going to do to make the attack more effective? Again, more pings. We were sending it 2 per second. That is every half a second. Just reduce the interval. Let's send at what? What do you want to send at? How many per second? 10? What's the minimum that you need? Well, remember, with 4 nodes sending, we don't have any more nodes, so we can't increase the number of nodes. We're going to have 4 sending. We need to reach 100 kilobits per second, so each of them should be sending at 25 kilobits per second. How do we achieve that? Well, all right, let's try, 5 pings per second would be 5,000 bytes per second, which would be, 5,000 bytes per second would be 40 kilobits per second. 5 pings per second would be 40 kilobits per second, times by 4 would be 160 kilobits per second coming in. Let's try it 5 per second. That is, the interval is 0.2. Okay, 5 pings per second. Send to the broadcast address. All right, just on node 5, its receiving should be 5 per second. What about node 7? ETH1 is coming into node 7. Remember, each one sending at 40 kilobits per second. We actually have 5 coming in, around 200 kilobits per second coming in. But coming out from node 7 to node 8, look at the amount being sent out. Because the capacity of the link is 100 kilobits per second, it cannot send any faster out. And our attack is successful. Well, at least we've overflowed the link, because the output link, ETH2, from 7 to 8, we're sending at 100 kilobits per second, approximately. That is, the pings from node 7 to 8, we've generated pings to fill up the bottleneck link of 100 kilobits per second. And that's our aim for the attack. Very easy in this case. Just ping to the broadcast address and everyone responds to the target. Questions on how that one worked? What if my capacity of this link was a megabit per second? What would you do? How would you fill up and utilize that capacity? What do you need to, if the bottleneck link has a higher capacity, what do you need from the attacker's perspective? Send faster, okay, send at a higher rate. So instead of 2 pings, 5 pings per second, 500 pings per second. Note that that requires some capacity from the source node, the attacker's perspective. So yes, we can send very fast, but that starts to use up the attacker's own resources. So yes, we can increase the sending rate. What else would enable an attack on the higher bottleneck link? Yeah. Change the protocol. Okay, how? I mean, what would the new protocol characteristics have? Like DNS, because
the request is much smaller than.
okay, if we had a protocol such that we send a small request, everyone receives that request, and then they reply, but the reply is much bigger than the request, make the reply large, more bytes, will increase the amount of data going to 8. So yes, a different protocol may enable us to do this amplification by sending small requests, requires just a small amount of resources from node 3, but generates large replies, which again overflows. Different protocol would enable that. If we're stuck with ping, what do we need? What else? Not in this network, in general. Increase the number of nodes. If we had a larger subnet, okay, we just send one ping, it goes to everyone on the subnet. So let's say the subnet was, say, for the SIT, one of the labs. Then there are 40 computers in the lab. You send one ping, all 40 computers reply and go to the target. So it's quite easy, in fact, in that case, to send one message and get many to reply using the broadcast feature. Let's stop this. Now, unfortunately for the attacker, using this feature of broadcast normally doesn't work in practice. Why? Because it's so easy to do a denial of service attack, send one message, everyone in the network replies. Most computer systems, most operating systems and network devices block such a feature. They don't respond to a ping to the broadcast address. So to set up this demo, I had to modify my operating system parameters such that it would reply. By default, these computers normally will not reply to such a ping request because denial of service attacks are very easy if they do. So normally routers will not allow a ping to a broadcast address. So this one will not send it out. And similar, if it did send out, these ones normally will not reply to such a ping request. So in theory, it's very easy to do an attack, but because of that, in practice, most devices will not let the broadcast message go out. So routers block these broadcast packets, and that happens in most cases. And in our demo, in fact, I had to modify 3, 4, 5, and 6 such that they would reply to the ping request that was to a broadcast address. I could do that. Note that 2 and 7 didn't reply. They were routers. I don't have a way to modify the operating system to allow them to reply. It's built in the operating system. Don't respond to them. So that's a countermeasure. So broadcast is a nice idea, but doesn't work much in practice. Okay, but what we can do is still, instead of using broadcast, I can still ping 4, ping 5, and ping 6, and they'll all reply. Let's do that. But let's do it now, and let's set node 1 to our malicious. Coming back to broadcast, we did broadcast from node 3 to its subnet. It would be better if node 1 could send one broadcast message to this subnet. Again, in theory it's possible, to send one ping, the destination is 2.255, it will go to all of these and all of these reply. If that was possible, someone out on the internet could send a ping message to the broadcast address for SIT. Every computer in SIT would then reply to the target. If that was possible, then a denial of service attack would be very easy. Therefore, most devices do not allow such a message to pass through. So if I tried that, send a ping to the broadcast, this one would block it. Say, no, you can't do that. So that's why I had to do it from node 3, just for this demo. Let's then get node 1 to individually ping 3, ping 4, ping 5, and 6 in parallel, and all of them reply to 8. Let's go back. Node 3 is no longer our malicious node. Node 1 is. Sorry. Node 1 is going to be our malicious node. Now for node 3 we need to remove this fake source address. It's back to a normal node. Delete this fake source address in node 3. We won't need node 3 at the moment, we need node 1. And let's give it a fake source address, same as before. And again to the address of the target, same as before. So node 3 is going to send packets, and it needs to send packets to 3, 4, 5 and 6 at the same time. So what you do is you just run ping in the normal mode, ping node 3, and then at the same time ping node 4 and 5 and 6. So to do that, actually, you need to open up 4 different terminals. Okay, you can do it, but to make it a little bit easier, I created a script that will do it automatically for us. So I created something called ping many, and it will ping as many nodes as I list. It takes, from memory, it takes the parameters of the interval and the size. So let's use our same interval as before, size as we used in the previous, and then we just set the destination addresses. So we want to ping 2.21, 22, 23 and 24. Ping many nodes at once. And it runs in the background. So we don't see any feedback, but we can see on node 7, is it working? Node 7, again, we're pinging 4 nodes, 3, 4, 5 and 6, and they're all replying to the target. Therefore, coming into the router, node 7 on ETH1 is 4 times, we're doing 2 pings per second, 4 times 16 kilobits per second, 64, and coming out around 64 kilobits per second. Now, we need more. We need to get up to 100. So as we did before, we just stop them and increase the rate. Reduce the interval. Now, those 4 pings are running in the background, so I need to stop them. And this is not so important, but I can kill them. Interrupt those ping processes. If you don't understand this bit, that's okay. Stop the pings. And okay, we're back to 0. So nothing's being sent. Now, remember, we're trying to stop normal users from accessing server 8. That's our aim. We want to overflow our link so that no one else can access 8. So what I'm going to do is open a web browser on node 3. I've set up a small website on computer 8, and I'm going to visit the website, and then we'll see when we do the ping how the response time is for visiting the website. Now, our nodes only have a command line, so I had to do some special setups to give a Firefox access. And I've set up Firefox so I can access the website on node 8. I've created a website on 192.168.3.31. Let's try. It's a great website. Just has a few links to some different pages. Okay, so this is think of this as the browser on node 3. It actually is using node 3 and sending to the target 8, which is 192.168.3.31. So this is the website on the target. How's the response time? Click on a link, no worries. Okay, it's very fast. Loads an image. Okay, let's go back. Now let's start our attack. But with a different interval. And an interval of 0.2 means 5 packets per second. 5 times 1,000 bytes is 5,000 bytes per second. 40 kilobits per second from one node. But we're pinging 4 nodes, so those 4 should respond generating 160 kilobits per second. 4 times 40. And our capacity is 100. We're sending at 160, so we should overload the link. Let's try it. Let's check. Is it working? Why is it slow? There we go. Coming in at around 160, going out the capacity of 100. Let's see on our browser now on node 3 the response. I'll reload. Note up here, it's loading the page. It's not responding very fast at least. Well, let's try something else. Let's try to a link to page 2. Connecting. Node 3 trying to browse to the target web server is getting no response. So the denial of service is working in this case. We're denied access to that website. It may connect, or it may... So why is it not connecting? So waiting down here. What's happening? We've got many ping packets coming into node 7. And it's sending out as fast as possible, 100 kilobits per second. And then node 3 tries to set up a TCP connection, so it sends a packet to node 7. But that packet has to wait for all those pings to be sent to node 8. So there's a large delay at node 7. There are many packets coming in, only some of them going out. The others are waiting in the queue to be sent, including the one from node 3 has to wait in the queue for a long time. Now maybe it gets sent and the response comes back slowly and then the request goes, or in the worst case it gets here and it has to wait so long that eventually it's dropped. It doesn't get sent at all. So that the request from 3 to 8 doesn't get there, or the response doesn't get back. We got to page 2 eventually, so it did load there. If we try page 6, again, you see the response time is very, very poor in this case. It's trying to send its packets to node 8, but all the ping packets are going to node 8. What if we stop that one and just modify a little bit, let's say 2.5 packets per second. So in this case, around, is this right? So again, around 100 kilobits per second coming in, 100 coming out. Now we can, there may be a little bit of delay, it's hard to notice, but again the capacity may not be fully utilised, so our packets are passing through. So we must, from the attacker's perspective, we must generate enough traffic such that the normal user's traffic is delayed a long time and even eventually dropped. And to do that, we just need to fill up that link, fill up the capacity. So that was around 80 kilobits per second. Questions?
Can Node 7 do a limit for the link request? I mean, for the link and that web server.
Okay, so how do we fix this? How do we stop such an attack? There are different ways. Yes, one thing that Node 7 could do is that it's receiving many pings coming in. So one thing that Node 7 could be set up to say, okay, my capacity here is 100 kilobits per second. If I receive pings at a larger rate, don't try and send them. Drop them immediately, so that the web traffic can get through. So give priority to some web browsing traffic going across this link compared to other traffic, the ping traffic. So yes, you could set up Node 7 to try and drop the ping packets. Let's look at the other issues. Just come back to our slides and see. Okay, so we've gone through, I think, we didn't demonstrate this attack. This requires a protocol that will send a bigger reply than the request. Ping doesn't. Protocols that do include DNS, SNMP for network management, a few other security protocols and network protocols. Network time protocol that synchronizes your clock on your computer does.
For the DNS, I need to have the DNS server.
Correct. For DNS to work, these hosts on the internet can't be normal hosts, they need to be DNS servers. So for a real attack to work, you need many DNS servers on the internet to attack. But there are a lot that will respond, and there are real attacks that use that. So it's not so simple that we can use any computer on the internet. But remember, there are, hundreds of millions, if not billions of devices on the internet. You just need some of them to respond. Thousands maybe, a small fraction. Sending to a broadcast address works real well in theory because you send one, many people reply, but in practice most devices block such packets. So it's not real useful in practice today. Everything up until now, these devices were not infected. That is, they were just normal computers on the internet. Therefore, it's quite easy to find computers to send via. But the next form is that the attacker gets some malicious software on some computers in the internet. Maybe many people have some virus that the attacker has programmed, and that virus initiates an attack. So the attacker takes control of computers on the internet. We call them zombies, where a collection of zombies is referred to as a botnet. It's a network of bots, and gets those zombies to initiate the attack. The zombies ping other computers on the internet and they reply to the target. What does the attacker need to do, and what resources does the attacker's network need? Well, all it needs to do is control the zombies. Send a special message to the zombies saying, start your attack on this target. It doesn't send the ping messages. It just sends one simple control message to the zombies saying, start to ping this target. And then they start pinging random addresses, usually in the internet. And if you ping thousands, some will reply and overflow the target. So a botnet contains many computers under the control of the attacker, which the attacker uses to initiate the attack on some target. And there's talk of botnets in the order of millions of computers in size. That some organisations have software on 1 million different computers, and they effectively rent that out to malicious people. So a malicious user goes to someone who has a botnet and they say, we'll pay you this amount per hour to use your botnet to attack a particular target. How do you stop that? Well, in practice, it's quite hard. It comes back to making sure, or limiting the chance of someone taking over the computer. That's important. So making sure that malicious software cannot be installed on these computers, antivirus and so on. And once discovered, there are some techniques to try and redirect the traffic. So if an attack starts, then the internet service providers can try and block the traffic before it gets to the target. But many real denial of service attacks use this approach. And again, from the attacker's perspective, they are hidden even further, because tracing back, the target traces these normal hosts, then going back, traces back to the zombies, and then from there you need to trace back to the attacker. So finding the attacker is even harder. In that case, the attacker needs to build this botnet, construct the attack network. They must get many slaves under their control. That is, many computers, so they need to infect those computers with some malicious software called some zombie software. So the general process is that they create some software that will do the attack, do the ping. It should run on different systems, different types of computers, so you can spread it across as many computers as possible. It should be hidden so that the normal user doesn't notice it. So the person sitting at this computer doesn't know that their computer is doing something malicious. And it should be able to be contacted by the attacker. So the malicious software sits there until the attacker sends some trigger saying, start the attack. Usually that then involves taking advantage of some vulnerability in that computer to get the zombie software installed on there. And then once you have zombie software on there, then you need to do that, you need to find machines that you can install the zombie software on. So scan for machines, infect them, and then the zombie software automatically searches for other computers to infect. So we can have it at different levels. So it's not just infect these 3 computers, but then they automatically try and find other computers to infect. And you get larger and larger. And that's how botnets of, say, millions of computers are created. To close, how do we stop all these attacks? And we're at what's called distributed denial of service attacks. A normal denial of service attack, think there's one computer doing the attack. But in fact, for practice, we have many computers doing the attack. They are distributed across the internet. So a DDoS, distributed denial of service attack. How do you prevent them? Have enough resources such that if an attack takes place that you can quickly allocate resources, network resources, server resources, so that if the load increases, that you can quickly adapt to that. But that's costly. Detect. So if an attack takes place, you want to detect it as quickly as possible so you can respond in some way. Respond. How do you respond? Identify who the attackers are. Try and take some action. Either block the packets from that attacker, but that more comes to, okay, contacting the internet service provider and getting the internet service provider to block those computers, or even take legal actions to stop them. It's usually hard to prevent a current attack, but you may prevent future attacks. So denial of service attacks try to prevent normal users from using the network, the system, the computer system, applications on those systems. You either exhaust CPU on the computer, or memory, or disk, or bandwidth in a network, for example, capacity. Often address spoofing, or using a fake address, is used to hide the attacker and to redirect traffic. Often we reflect packets off normal hosts to amplify the amount of data going to the target by using protocols that send small requests and large responses. Use other computers under your control that are infected with some software to initiate attacks. Generally quite easy to perform. We did it quite easily on a virtual network. Hard to prevent, but easy to detect. But often detection is too late, because if you're Amazon and the attack even goes for 1 hour before you detect or before you can respond, then that's 1 hour of lost money, lost income. So that's still a significant problem in the internet. Have a look at some of the other areas to explore. We will not cover through them if you're interested further. Any final questions on denial of service attacks? We've gone through demos of just some very simple ones, but show the main concepts used by most. Try, if you like, the demo that I did. You may be able to modify, you may be able to even do attacks with different protocols. I think you could try DNS or NTP to do even a more advanced attack. But of course, if you try anything, just do it in a virtual network. Never do it in a real network. Okay? And it's very easy to do it. Yeah?
You open the link software.
The instructions for everything I did are linked to from the course website. Okay, so you can read everything that I did there, all those commands, so you can copy and do it yourself. You can read through all the commands, and this is linked to from the course website. The steps for creating the network and the commands for setting up the nodes, and for example the commands for doing the fake source address.